Okay, welcome to Mechanical Engineering Systems. In today's class, I'm going to talk about uh, turnbuckle design and power screws design. And if there is some time left, then I will talk about the lever design and or spring design. So far, we have been talking about design of cotter joint, design of knuckle joint. And the purpose of cotter joint or cotter joint or knuckle joint is used to join or connect rods. Now, if you look at the structure of the cotter joint or knuckle joint, you would observe that if you have a rod on the left hand side, if you have a rod on the right hand side, neither cotter joint nor knuckle joint allow any provision for adjustment of the distance in between these two rods. So it is not difficult to visualize that you can have a cotter joint which could get unnecessarily stretched or compressed because of the distance between the two rods is not accurately maintained. So what is the solution? The solution is something called as turnbuckle. So turnbuckle. And most of you have seen this turnbuckle, and there are different ways this turnbuckle can be manufactured. So for an example, what you have is you have a screw, say it is left-handed screw on one side. You have screw that is right-handed on the right-hand side. So essentially, you have screws that are opposite oriented. So what it means is if you turn or rotate one screw, depending upon whether it is clockwise or counterclockwise, whether it is right hand or left hand, either the screw will advance or the screw will retract. And what we have is on top of it, you have something like this. So you have a matching thread. So you will have a left hand thread on the left side, and you will have a right hand thread side. Look at to draw, it would look something like this. And I'm gonna sketch. This is the shaded area. So this is left hand and this is right hand. So what it means is, and this is called as the nut. Whether you rotate the nut in the clockwise direction or counterclockwise direction, these screws on the left hand side and on the right hand side, they advance or retract. And then you have your rods over here. So this is the rod on the left hand side, this is the rod on the right hand side. And in turnbuckle design, what we want to do is we want to find out the dimensions of the screw, dimension of the rod, dimension of the nut. Now I just want to show you sort of a magnified view of the screw. So there are different types of threads. You could have a V thread, you could have a square thread, you could have sort of an acme thread, but I'm gonna, just for the sake of discussion, for simplicity, I'm gonna show you a very simple thread pattern. So this is a very simple thread pattern. And what I want you to observe is this thread it's sort of a helix. So what it means that if you start from one end and if you were to continue traveling, then finally you're gonna go to the other side. But you will be traveling on the circumference. Now, if you look at the front view, you're gonna observe it will have an inside diameter, and it will have an external diameter. So there is something called as DI, which is also called as core diameter, which is called a DC. So this is core diameter. And then this is DO, which is outside diameter. Now, if you look at the weakest cross section, the weakest cross section is over here. So I'm gonna just highlight this. This is the weakest cross section. So this is the least area. So which means if I want to look at the failure of the screw under loading, and I'm just going to assume turnbuckle can support compressive or tensile loading, but for the sake of discussion, I'm gonna say that there is tensile loading P, tensile loading P. So the area that is going to resist the tensile load is nothing but this core area. Now there is something else I want to talk about. Now please understand, when we have a screw and nut assembly, when we have a screw and nut assembly, so nut plus screw assembly, that is used for power transmission, application, it's called as power screw. Now you would see power screws in a lot of applications. A very simple application is if you look at the 3D printer, the 3D printer has typically 3 slides. They go X, Y, and Z direction. So you will have sort of a long screw, and you will have a stepper motor that will be attached at one end of the long screw. Then this is the screw, and here there would be a nut, and as this screw rotates, or in other words, as this motor rotates, this nut will go forward or backward. You can have a vertical assembly. So rather than horizontal assembly, you could have a vertical assembly, and up and down motion of the nut can be controlled by the motion of the motor. So this is called as the lead screw. If you look at different machines, for an example, 3D printers we talked about, lathe, milling machine, CNCs, wherever you have to transfer the rotary motion into linear motion, and that linear motion is typically used to transmit power. And just to define what power is force times the velocity. That mechanism that can be used is called as power screw. Now, power screw depends upon the theory of friction. Now, there is another example I want to talk about briefly before we actually look at the theory of power screw. Is I want you to think about the screw jack. So if you look at the screw jack, I'm going to show you a very simple diagram of the screw jack, you will have a screw jack body, you will have a screw jack nut, and then there's an actual screw. There's an actual screw. And this actual screw and now I want you to visualize that there is a handle here. So if there is a handle here, if I rotate this handle, depending upon uh, the lead of the screw, that means the amount of linear travel in one rotation, this platform will be raised up or it will go down. And we will talk about the precise definitions of lead and pitch and everything. But what I want you to observe is there are two cases possible. The first case is you raise the load. So raising the load, raise load, and remove the torque. So just to give you an idea, consider that there is a load W. And to raise this load, you will have to apply torque T. And what happens is you raise the load to a particular height, say H. And if you remove the torque, what could happen is the load would remain where it is. So load is not going to move. So if you raise the load and remove torque, there are two cases that are possible. So first and foremost, the load stays where it is. Load stays at location. And the second case that is quite possible, is load runs down. What I mean by that is all of a sudden, just because of the weight, the screw jack starts getting lower. So basically, you raise the load and then leave the torque, then on its own, the screw unwinds and the load comes down. So that is called as rundown. And this is a very common application if you want the screw jack to be used as a clamp. So for an example, if you have two pieces of plywood and you want to make sure that these two pieces are glued together, then what you do is you used a screw and nut assembly that sort of is a rundown. So what it means is you rotate, apply torque, raise the screw, place the plywoods, release it, and on its own, the load comes down. So on its own, load comes down. And the second case is you remove the load, you remove the torque, and the load stays at whatever location it is. Now, why this thing happens? Why would something like this phenomenon happen? And what would dictate whether it's sort of a rundown load case or is it a load lock case? And the single important reason here is the relationship between the friction and the helix angle. So friction and helix angle. Now the power screw theory is dependent on the angle of friction and the angle of helix. Now, before we talk about the friction angle and its relationship with the helix angle, I just want to give you a very simple outline of the power screw. So if you look at the power screw is sort of a helix. So the way the screw is cut is you have a cutter, you have a rod stock, and then you basically turn it to construct this groove, which is actually has the core diameter and the outside diameter. So this angle is called as the helix angle. Now, what does this helix angle mean? It means if you were to start traveling at this location, you're going to go all the way from here, you're going to come from the back, and then you're going to come back, and then you will continue to travel on the screw. And the angle that the screw is going to make is nothing but the helix angle. Now, just for the sake of simplicity, imagine that you wrap a thin strip across the thread. So what I'm going to do is I'm going to take a thin strip of paper, or you can take thin a strip of aluminum foil, or you can just take a thin wire, and if you wrap it around, and say if you expand it, so you wrap it around, and then if you just expand it, you would observe that this wire is going to look something like this, or this thin strip would look around something like this. And I want you in your mind to think about this exercise. Consider that you have a cylinder. Just imagine that you have a cylinder and try to wrap this triangle around this cylinder. And you will realize the point that is traced on this cylinder is going to be at an angle which will be the same angle as the helix angle alpha. So alpha is the helix angle, and that helix angle is nothing but, if you look at the thin strip of paper, this triangular paper, and you wrap it around the cylinder, then it will actually trace a helix. So helix angle is quite important design parameter in the case of power screws. Now, next thing I want to talk about is something called as the friction angle. Friction angle. And I'm sure all of you studied concepts in friction in EGR 217, but just let me quickly recap what friction is. So friction depends upon the two areas in contact. So coefficient of friction depends upon the surfaces in contact, force of friction or frictional force, depends upon the normal reaction multiplied by the coefficient of friction, where mu is the coefficient of friction, n is the normal reaction. Now, coefficient of friction and even frictional force does not depend upon area. So the frictional force is independent of area. Now, one thing that is very commonly asked is, how can we find out coefficient of friction? So how do we find out? How to find mu experimentally? Now, characterization of mu itself is a huge field of study and analysis. But what I want to give you here is a very simple idea to estimate the coefficient of friction. Now, what I want you to do is I want you to visualize this experiment. So what I have is I have a plate. I have a plate that is hinged at one end, and I have a block. The mass of the block is m. So this is the block. This is the hinge. And think about this. This is the plate. And you are looking in the front view. Now what I'm going to do is, as you can see, at this particular orientation, the plate is completely horizontal. So which means the angle made by the plate with respect to horizon is 0. Now I want you to imagine what would happen if I start rotating, or if I start increasing the angle of inclination. So initially I make plate go like something like this. Then I would make plate go something like this. And remember that this experiment is performed very slowly. So very slowly change theta. And I'm going to call this theta. Very slowly change theta. You would observe that for certain value of theta, the block will start going down. At certain value of theta, the block will start going down on its own. So there is a threshold angle theta. So I'm going to call that threshold angle phi. At phi, block at phi, so this is the limiting value of theta, limiting value of theta, at which block just starts moving. So what's going to happen is there is going to be some angle phi. At that limit value, this block would start going down. Now, assuming that you visualize this experiment in your mind, I want to change a few things. Now, what I want to do is I want to add a thin layer of oil on this plate, a thin layer of oil. If I add a thin layer of oil, what would happen to the angle phi? If I add oil, what will happen to the angle phi? If you visualize, the angle phi would be less than the original phi when there is no oil. So phi with oil will be less than phi on dry. What that means is the block will start moving down on its own earlier when there is oil. Now, what is the meaning of oil? When you have oil, what is the meaning of adding oil? Which means we are reducing friction. So what happens is this limiting value of phi is somehow dependent on the actual value of friction between these two surfaces in contact. So the way we find the coefficient of friction is we place a block on the surface and gradually tilt the surface to a limiting value when the block just starts sliding, and the angle that we get is called as the friction angle. So phi is also called as friction angle, and mu, which is coefficient of friction, is given as tan of phi. Now what I want to do is I want to write the conditions of static equilibrium to derive this equation, but here is the key takeaway. The key takeaway is when the coefficient of friction is low, either you have used different material or you have added lubrication that reduces the effective coefficient of friction between two contacting surfaces, the friction angle reduces. The reduction in friction angle means the motion of the block could begin earlier. So what I'm going to show is I'm going to show the case when you have this limiting angle. So theta is equal to phi. And I'm going to draw a block here. Block has the mass m. It has the gravitational force mg going down. Please note that we need to resolve the forces in the perpendicular direction to the block and in the parallel direction to the block. So this force is going to be mg sine of phi, and this force is going to be mg cosine of phi. Please note, this is the limiting case when the block just starts sliding. So condition here is the block just starting to slide. Now assuming the coefficient of friction between the block and the surface, the coefficient of friction is mu. So the coefficient of friction is mu. And please note, coefficient of friction is dimensionless. It does not have any other dimension. So the frictional force that is going to oppose the motion, the frictional force, and I'm going to show this frictional force like this. Frictional force that is going to oppose the motion, F, is nothing but mu times the normal reaction. So this is how I have forces in the x direction and y direction. So I have resolved the forces in the parallel direction to the block and the perpendicular direction to the block. So I'm going to sum. So I'm just going to call this x. I'm going to call this y. And I'm going to say summation of forces in the y direction is equal to 0 because the block is just about to start moving. So you have the normal reaction, and that normal reaction n is going up. Normal reaction n is going up. So plus n minus mg sine phi. That tells me the magnitude of the normal reaction is mg cosine phi. It's about y. So this guy, mg cosine phi and summation of forces in x direction is equal to 0. That means the frictional force, which is positive because it's in the same direction as positive x, minus mg sine phi. That tells me F is equal to mg sine phi, and F is nothing but frictional force. And we know the relationship between the frictional force and the normal reaction, and that relationship is given over here. F is equal to mu n. So I can write this equation mu, and please note value of n would come from here. Mu times n is mg cosine phi is equal to mg sine phi. What that means is mu is equal to tan phi. And this is an important relationship. So coefficient of friction mu is nothing but tan of the friction angle. Any questions at this point? So what I want to do is, now I'm gonna take the two cases. One is the self-locking screw, and so load running screw. Again, self-locking screw means the load stays or locks when external torque is removed and load running screw means load runs down when external torque is removed. And there are specific applications. You will see self-locking screws are very commonly used in screw jacks for raising loads, and load running screws are usually used in the punch presses or brakes, self excited brakes, so or the brakes, wherein say in the case of power failure you don't want a lift or something to go down. So I'll give you a very simple example. Imagine what happens in the case of brakes is there could be a case wherein you have to continuously apply power so that the system stays in place. For some reason, if the power is removed, it needs to go back to its rest position, which is touching the ground. Now, what are the cases in the case of self-locking screw? I want you to visualize the same example that I talked about. That you have a plate. On this plate, there is a block. And in the case of self-locking screw, the friction angle is this. This is the friction angle, which is phi, and the helix angle is less than the friction angle. This is alpha. So as you can see, is at phi, the load will start going down on its own. But since our helix angle, the actual angle of the plane, is less than the friction angle, since alpha is less than the friction angle, the load will stay wherever it is. So at this location, if the load is here, what that means is the frictional force that is over here is greater than the component of the self weight that is pulling this load down. In the case of running screw, you would observe same case. You would observe that the friction angle phi is less than the helix angle alpha. So in other words, alpha is greater than phi. Where once again, alpha is the helix angle and you have this friction angle. So helix angle is greater than friction angle. Now there is a case that is possible in between. Consider a situation where you have a self-locking screw. And that self-locking screw, the way it is designed, in that case, your alpha is less than the friction angle. But something happens and this surface becomes super slippery. So maybe you add oil or something changes, there is some grease. And what it does, it effectively decreases the friction angle. As friction angle is tan inverse of coefficient of friction. As the coefficient of friction is decreased, friction angle is decreased, and then in that particular case, self-locking screw becomes a load running screw. So whenever you design the self-locking screw, you have to make sure that you have enough factor of safety so that even if there is some water, even if there is some oil, even if there is something else going on, the coefficient of friction should not decrease to such a level that the load on its own will start running down. So that this is an important concept in the power screw design. The last thing that I want to talk to you about is nothing but the pitch and the lead. So lead is advance of nut in one revolution of screw. So I want you to visualize this. So you have a screw and there is a nut. So the lead means how much is this nut going to travel in one revolution of this screw. So the relationship between the lead and the rotation is very important. And this is given as something called as the pitch multiplied by number of starts. So lead is equal to pitch of threads multiplied by number of starts. Now, what does this mean? Depending upon the application, you could have a single start screw. In the case of single start screw, you just have one helix that goes around the screw. So what it means, in one revolution of screw, the nut is going to travel forward by just one pitch distance, and I'm going to call this P. So distance between the successive threads is P. So this is the pitch. But sometimes what happens is you could have, this is single start, and you could have a multi-start screw wherein two threads run parallelly. So, and it's difficult to draw them. So what I would recommend is you just take a picture online on a web that will show you how those threads are. So basically you're going to have two threads running parallel. So this is double start. Now what does that mean? It means in one revolution of nut, in one revolution of screw, lead is going to go forward, the nut is going to go forward by 2 times the pitch. So always remember this equation, the lead is equal to pitch of the thread, which is nothing but the distance between the successive threads multiplied by number of starts. Now, when do we use multi-start screw? Say for an example, if you want your slide to advance quicker, say if you have a single start screw, in one revolution, you will travel the distance P. If you have a double start screw, in the same revolution, in one revolution, the nut will travel 2 times P. So which means for the same amount of revolution, you will be traveling farther. So if you have particular requirement on distance to be traveled in the revolutions of nut, in the revolutions of screw, or if you have particular condition on the velocity, then you would use multi-start screw. And for simple applications, for an example, if you look at the bolted joints, or if you look at a simple screw and nut assembly, they will not have multi-start screw. The advantage of multi-start screw is only when you want the motion and force to be transmitted. If you just have a nut, screw, and washer assembly, say for example, if you have a washer and then you have a base plate, and then what you have is you have a nut and a bolt. If you have a nut and a bolt, so what you do is you drill the hole, and then you have this bolt that is going in, and then what you do is you add a nut, a small nut on the other side. So you have the bolt, you have the washer, this is the base plate, and then this is the nut. So if you have nut, bolt, and washer assembly, you will not see double start screw, because please understand this is a static operation. So the entire assembly is going to remain in this condition all the time. In this particular case, the nut and bolt assembly is used for joining purposes. So it's a bolted joint. This is called as the bolted joints. It's a bolted joint. For bolted joints, you will not have double start screw. The advantage of double start screw is in power screws or when the motion is an important characteristic. So that gives me an expression for the helix angle. So how do I find out the helix angle? Helix angle alpha is given as tan inverse of lead divided by pi times diameter of screw. And I have to be careful here. I'm gonna call this DM because this is called as the mean diameter. So what I want to do is I want you to visualize the same paper that we wrapped around the screw and visualize that in one revolution, it's gonna go up by lead, and this distance is corresponding to one 360-degree wrap or one single revolution, so which is pi times dm. Now what is this dm? Please understand that if you look at the screw geometry, usually screw will have an outer radius and the inner radius, or outer diameter and inner diameter. So dm is nothing but the average do plus di divided by 2. Di is the inner diameter, which is same as core diameter, dc. Inner diameter is same as core diameter, dc. Okay, so helix angle and friction angle, they are important parameters and they dictate the design of the power screw. You're gonna have an outside diameter, which is do. You're gonna have a core diameter, dc. So when you want to find out the angle, helix angle alpha, you will have to find out the tan inverse of lead divided by pi times dm, and lead is equal to number of starts multiplied by the pitch of the thread, and we'll solve few problems. In that case it will be clear. Okay, any questions on the material discussed so far? So one important question that uh, needs to be thought about is, if you have a threaded joint or if you have a power screw, what type of stresses uh, are observed in power screw? Now, before we answer that question, I want to answer a very simple question, and this is, given the load W, so this is the question, given the load W, coefficient of friction mu, and the helix angle alpha, and assuming the mean diameter of screw is dm, this is the mean diameter of screw. What is the torque required to raise the load? So the question is, consider that you have a screw jack. This is just a schematic diagram of a screw jack. And on this screw jack, there is this platform. On this platform, there is this load W. So this is the load W. And this load is given in newtons. Now, to raise this platform up, I need to apply some amount of torque. So to raise this load, I need to apply some amount of torque. Now, how do I find out how much torque I should be applying so that the load is raised? And please note, I'm not talking about the power or the work. I'm talking about just the amount of torque that is needed to raise the load. And that equation that I want you to remember is nothing but, again, it can be derived from the triangle that I have shown on the right hand side. T is equal to W multiplied by R. So W is the downward force or the weight. R is the radius, and I'm going to call this Rm, which is the mean radius. Tan of phi plus alpha. Now this equation, I will explain once again, will be used in lot of applications. This equation is used in turnbuckles. This equation is used in power screw. This equation is used in design of screw jack. You will see this equation is used when you are designing uh, the slide for the stepper motor or 3D printer. So what would be the torque capacity of the stepper motor if you want to raise the extruder continuously? Or what would be the capacity of the stepper motor if you want that stepper motor to move the load W? This is also used in the determination of the motor power for the lathe. So wherever you see power transmission applications using screws, this equation is used. So let me define the terms. Alpha is the helix angle. So alpha is found out with the equation tan inverse of lead, which is n times pitch divided by pi times dm. Phi is the friction angle, which is tan inverse of mu. W will be given in the problem. Rm is nothing but dm divided by 2. dm divided by 2. And dm is given by this expression. So this is a very, very important equation that we will use multiple times in different chapters. So remember this equation. Torque needed to raise the load or to move the slide is weight that is to be moved multiplied by the mean radius multiplied by the tan of the combined friction angle and the helix angle. Any questions here? Now the next question that arises is, what are the types of stresses at this interface? So the question is, what are the types of stress? So what type of stress do you expect when you have a power screw? Now, just to give you an idea, power screw can be used in vertical application or in horizontal application or an inclined application. So what it means is power screws can transmit tensile loads and compressive loads. So power screw can transmit tensile load and compressive loads. So first and foremost, let's start with a very simple case. And what I'm going to do is, I'm going to try to maybe draw a power screw horizontally. So this is the power screw, and I'm drawing this horizontally. And I'm going to show you the nut that is assembled on the other side. I'm going to show the nut that is assembled on the other side. And then you will notice that the nut will have internal threads. So this is nut. This is screw. The screw will have external threads. The nut would have internal threads. And clearly, if the screw is right hand, your nut has to be right hand, because right hand screw and left hand thread, left threaded nut will not match. You cannot assemble those. So now you have this assembly. And then imagine there could be a tensile load on the nut and the screw. So there could be a tensile load T on the nut and the screw. There could be compressive load on the nut and the screw. So you could have this joint or this assembly is able to sustain tension load as well as compression load. Now I want you to add one more thing to it. Under the action of load, if we want this assembly to transfer forces, I'm going to apply torque. So notice that in this case, I have a load, either tension or compression, plus torque that is simultaneously acting in the case of power screw. Now this case is different when the nut and bolt assembly is just used as a bolted joint. When the nut and bolt assembly is used at the bolted joint, once you torque it, at that time you are going to have some amount of torsion, some direct loading. But once you leave it, then you remove the external torque, and that whole assembly is going to be subjected to static stress. So you will not have simultaneous action of tension or compression forces and torque. So just to give you a quick idea, tension and compression give you normal stresses. So you are going to have sigma. Torque gives you shear stresses. So now you have a case where normal stresses and shear stresses act simultaneously. And when normal stresses and shear stresses, they act together, what do we get? We get principal stress and we get maximum shear stress. Now we spent significant amount of time on talking about normal stress and shear stress and their application. So principal stress is nothing but the equivalent normal stress when you have simultaneous action of normal and shear stresses. Maximum shear stress is the equivalent shear stress when you have simultaneous action of normal and shear stress. And for completion, I would give you the equation. This is a design class, so we are looking just at the maximum stress, sigma plus square root of sigma square plus 4 tau square 1/2. And tau max is equal to 1/2 square root of sigma square or tau square. So remember these equations. So whenever you have a screw joint and that is used for power transmission, you will use the principal stresses and you'll make sure the principal stress is less than the design normal stress, and the maximum shear stress is less than design shear stress. And when I talk about what do I mean by design stress, remember we talked about the failure criterias, and we talked about something called as the failure of mild steel stress strain curve. So what you have is you have something called as the yield stress for ductile materials, and the design stress design is yield stress divided by factor of safety. Factor of safety. Many a times these values will be given to you, but if they are not given to you, you can refer to the data sheet, or you can refer to the design data handbook, or you can just look at the material properties and find out the appropriate values for the design stress. So this is the basic theory of operation, or theory of and the analysis for the power screw. Now what I'm going to do is I'm going to give you a recipe for design of turnbuckle. So let's look at the design process for the turnbuckle. And these turnbuckles are super common. For an example, if you go watch a pole power line support, say for an example, if you walk around the campus, you will see that there are power lines, and then you will observe that to support the power lines, there are steel ropes, so steel rope, and then at the end there is a turnbuckle. And the reason for turnbuckle is to adjust the tension, because this rope over a period of time could actually stretch, and then in that case what you do is you have this turnbuckle that you can adjust. So basically you put a rod through this hole and rotate it and then adjust the loading or the tension on the pole. So this is the electric pole. This is the rope, and you have a turnbuckle that can adjust. The other interesting thing, if you look at the turnbuckle, if you go to the student activity center, and there is a staircase from the first floor to the loft, and if you look at the sides, there are ropes going through, and at the end of the ropes on the staircase that goes from the first floor to loft, you would see turnbuckles that are in the place so that to adjust the tension in the rope. So you will see numerous applications of turnbuckle. If you look at the car, the turnbuckles are used at different locations just to maintain the distance and combine or transfer tension and compression loads. So what I'm going to do is I'm going to give you a step-by-step recipe for design of turnbuckles. So I'm going to use, just for the discussion, a simple solid nut. So this is the turnbuckle. And the thing with the turnbuckle is the rods, they don't have to have the exact same diameter. I've seen cases when the rod on the left-hand side and the rod on the right-hand side, they have different diameters. As long as the whole assembly is capable of supporting the desired load and it's not failing, that is okay. So you could have the rod on the left side with different diameter. You could have the rod on the right-hand side with different diameter. But please note the directions of threads, they have to be opposite and they should match with the same orientation of the threads. For an example, if you have a left-hand thread on the left-hand side, then the nut that meshes with the left-hand threads should be left-hand and they should be opposite. So if you look at this nut, this is the simple nut, and sometimes you could have some sort of a hexagon shape outside so that you can actually use a wrench to tighten this or adjust the distance, or sometimes you could have a hole through the center that allows us to insert a rod and then basically rotate the nut. So this diameter, and there are some variations. So depending upon the design, there are some variations possible. But what I'm going to do is I'm going to give you a design recipe for a standard turnbuckle that can be slightly modified depending upon what we are trying to design. So I'm going to call this diameter as D. Then I'm going to call this thickness T. And I'm going to call this diameter D1. And I'm going to call this diameter D2. And again, it doesn't have to be a diameter. The shape could be different. And one quick note is the nomenclature that I used could be different than what is used in the textbook. So if the nomenclature is slightly different, that's okay, as long as you are referring to the same dimension. That's what matters. Also, sometimes the design procedure that I outline could be slightly different than the procedure that is given in the book. Now, and again, that is acceptable because typically the design is art and science. So based on the experience, based on the uh, what theory that you use to design, your design dimensions could be different or the governing equations could be different. But at the end of the day, there is nothing like right or wrong answer because you want your design to be safe. As long as your assumptions are correct, you can justify why you use this particular approach and then show that under the loading, uh, all the dimensions are safe, no component is failing, that is good enough. And the design process that we are going to discuss in the class is a classic uh, pen and paper design that uses the theory of strength of material or simple principles from uh, mechanics of material. But what we do is once we have these basic dimensions, to finalize the overall design, we expand upon these preliminary dimensions and then perform a finite element type of analysis at the component level and at the assembly level, just to make sure that the design is safe. And about 10-15 years ago, uh, there used to be something called as drafting. So you would have something called as a scale, and then slide rule and all other drawing instruments that you will use to draw by hand the drawings and apply the dimensions. That is called as the design blueprint. But nowadays, all the designs are done on computer software. So you can create the 3D model, and then the software is capable of generating the design drawings. And that is the process that is currently used. So these dimensions that we find out from sort of the back of envelope calculation, they are verified using computer software or a finite element method. Okay, so objective of this design exercise is to design the turnbuckle, and I'm gonna give you some uh, problem statement. The load on the turnbuckle. So load on turnbuckle is P Newton. This is the design criteria that our turnbuckle should be able to sustain this load. And then we will give you the values of the design stresses. So design stresses are known. Are given. If design stresses are not given, in other words, sigma design in tension, sigma design in compression, tau design in shear, sigma design in bearing, they will be given to you. If these stresses are not given, then the material would be known. So for an example, the material for the rod, it say material is mild steel, and the material for the nut is alloy steel. So then what you do is you look at the design data book and find out these values. So find using data books. Sometimes the problem could be open-ended, which means the material also may not be specified. They will just say design the turnbuckle use for the load P, and they will give you the application. So what you need to do is, for applications, so you would choose the appropriate materials. So materials can be selected based on applications. So a simple example is, if you have to use a turnbuckle in kitchen, or where the cooking or there is continuous human contact, you don't want to go with a material that can cause maybe any reaction. So you would most likely use a stainless steel. Or if you want to use a turnbuckle in a super corrosive environment, then you want to use the material that is that can resist the corrosion. Maybe use nylon or maybe use some sort of plastic. So depending upon the particular application, you will have to choose the material, and with that material you will choose the stresses. And again, this material guideline are in design data book. Or it's also called as machinery's handbook, or it's also called as design data. So you have to select appropriate material and stresses. Okay, 7:16. I'm gonna give you 15 minutes break, and after the break, we will continue the discussion on design of turnbuckles. I'm gonna pause the recording. Okay, so now I'm gonna give you a design recipe for the turnbuckle. You can follow this recipe to design the turnbuckle and then check for different types of failures. So step one is to find out the core diameter of the rod. Step one. Design core diameter of rod. Now, assuming the turnbuckle is in tensile failure, so failure is in tension. Sigma T is equal to P divided by A, where P divided by pi by 4 dc square. And from this, we should be able to find out the value of the core diameter. Now, core diameter again, if you look at the screw, you have an inside diameter and an outside diameter. This is the weakest section. So the core diameter is this. And once you have the core diameter, you can find out the relationship between the outside diameter, DO, is equal to outside diameter is, and DC is usually 0.8 times DO. In certain cases, you can have a slightly smaller DC. So it can go anywhere between 0.75 to 0.85. So once you find the diameter of the rod, then what we need to do is we need to determine the helix angle and find out the force that is needed. So step two, torque needed to rotate buckle. And I'm going to call this T. And the reason we need to find the torque, because this torque will help us find the value of the shear stress and the maximum shear stress and the principal stress. So torque is equal to P multiplied by M tan mu plus phi. Now please note, at this point, lot of quantities are unknown. So let's find out what is known. So in step one, I find out the value of DO and DC. So I can find out the value of DM as DC plus DO divided by 2. RM is equal to DM by 2. This P is the load that needs to be supported. So this P is known, this RM is known. I do not know the value of mu and phi. Now mu can be taken, or value of mu depends upon the materials that are in contact. And you can use the design data book for the appropriate coefficient of friction. Now usually the value of mu can go anywhere between 0.2 to 0.3. So for an example, if the value is not given to you, there is no harm in just selecting the value of 0.3 and saying that, assuming steel to steel contact, the coefficient of friction is 0.2. So with this information, I can find out the value of phi as tan inverse of mu. And one thing I want you to understand, that with this equation, this value you will obtain in radians depending upon your setting in your calculator, but this value is in radians. Then to find out the value of alpha, so this is alpha helix angle, and this is friction angle. So please note I made a mistake. It's alpha plus phi. So I can find out the value of phi, and now we have to find out the value of alpha. Now alpha usually depends upon the design parameters. Uh, so typically tan alpha, I have seen the values of alpha go from 7 degrees to 14 degrees. And many a times they will tell you that this is the helix angle that we want to use. And the reason for that is we don't custom cut threads. We usually go to MacMaster or some other vendor and look at the rods and the screws that are standardized and available. So there is something called as ACME, American Screw Manufacturers Association. They have their own standards. So typically those standards are followed when the screws are cut. So the idea is, once we find out the value of, once we know the value of P, we find out the value of Rm, we find out the value of tan alpha plus phi, we get the value of external torque. Now, the next step is, please note that this sigma t allowed us to find the value of DC. But this value of DC most likely is going to be in some decimal points. So like 23.4 or 22.7 or 28.9. So before you go further, you will have to round this off. So this will be rounded. So round of DC. And what that means is the actual stress will be less than the design stress in the rod. So what you will do is, and I'm gonna just call this round of DC, and I'm gonna call this DC new. So what I would do is, I will find out the value of sigma using the DC new. So I will do pi by 4 DC new square. So now this gives me the value of sigma. Now please note I have the value of T. I have the value of torque. Now with this torque, I can find out the shear stress using the equation for torsion. So, note value of T is known from the previous step, from previous step. Value of dm is known from step 1. So that allows me to find out the value of tau, which is T divided by J multiplied by R. So this screw is a solid screw. So this will be pi by 32 dm to the power 4 multiplied by dm divided by 2. And that will give you a value of torque, value of shear stress. This shear stress will be in Newton per millimeter square. Please note, here also we found out the stress that is in Newton per millimeter square. So at this point, value of tau is known and value of sigma is known. And these two stresses, they act simultaneously. And then that allows us to find out the principal stress and the maximum shear stress. And this should be less than sigma design, and this should be less than tau design. Now, I just want to give you a word of caution. This process, what I have described, is the standard process. This is the standard process, which means I'm going to use the exact same process when I design the power screws. So for an example, when I'm going to design the screw jack or when I'm going to design the scissor jack, I will use the exact same process. However, if you refer the textbook gives you a shortcut. So there is a shortcut approach in textbook. And what it does is, for the turnbuckle, they use the standard dimension as tan alpha is equal to 0.03 and tan phi is equal to 0.2 and some other standard dimensions. And then they give us this big equation for sigma. And this equation is approximately, this equation for sigma p principal stress is approximately 0.5 times sigma plus 0.707 times sigma. And this expression is approximately 1.25 times P divided by A. So if you refer the textbook, you will observe that the textbook approach is slightly different, and then they use this particular equation to find out the principal stress. However, I would recommend not to use this approach. So do not use this approach. And the reason for that is, if you look at the screws uh, depending upon the values of alpha and depending upon the value of phi, this relationship may be different. And in the case of special purpose turnbuckles, it may be possible for us to use this equation, but in general, this equation cannot be correct. So don't use this approach. Instead of follow the approach that we have talked about by assuming the value of mu, by assuming the value of helix angle, and then finding out the value of torque, then finding out the values of shear stress, uh, recalculating the value of normal stress, and then using these tau and sigma values, find out the principal stresses and the maximum shear stress. Any question? Now, next design dimension is the length of the nut. Step 3. Length of nut. Now, there are multiple approaches that this dimension can be found out. So before we talk about this dimension, let's talk about the failure. And I'm just going to show a failure on one side. So we have this rod. This rod is threaded. And then you have this nut. And imagine you have the same assembly on the other side. So consider that there is this load P, and then there is this load P. Now, if you look at the way this nut and the rod assembly or the screw assembly could fail is if at the nut and the screw interface, if there is interface crushing. So there are two ways this can fail. This could actually crush at interface. So what could happen is, so you have this outer thread, you have this inner thread, and then there is this nut that goes around, and you will notice that this area gets crushed, and that would result into the failure and locking of the assembly. The other way that this whole assembly can fail is, think about it, is the screw comes out. So basically this ring comes out from the screw dimension. So the screw remains as is, and this ring, which is nothing but the thread, so the thread gets separated. And this failure can also happen, actually it will happen at here, and that will be because of the shear failure. So there are two types of failure that are possible. One is the shear failure, and the other one is the crushing failure. Now this nut is actually symmetric on both sides. So I'm going to say this is the length of the nut. So I'm going to call this L by 2, because on the other side, I'm going to assume that you have the same nut. So P is equal to pi times dc times L. Actually, let me write this equation slightly differently. Tau, shear stress, is equal to P divided by pi times dc times L. And this actually would be L by 2. So this is the length of the nut. And to be consistent, this is capital L. This is length of the nut. Now I can try to find out the same failure, but in crushing. So if you look at sigma c is equal to P, which is the external load. Now crushing area is pi by 4 d outside square minus d inside square. And please note, there are multiple nuts in engagement. So you are going to have, that is N. These are the number of threads in engagement. Now, one thing that you may ask me, that how does this give me the dimension? So let's go through this process just once again. So they have given us the value of P, which is the external load. And this external load could cause the shear failure or can cause the crushing failure. If you look at the shear failure will can give me directly value of L. So in this equation, everything except capital L is known. So I can find out the value of capital L. However, when I look at the crushing, please note there are multiple uh, threads in engagement. And remember this, for a continuous engagement or for sort of a good engagement, minimum 3 complete threads should be in contact. Otherwise, you will not have a good engagement. What do I mean by not having a good engagement? And you can visualize this. Consider that you have a nut and you have a bolt, and the bolt is just one thread engagement. So this is the hole, or this is the tab, and this is the bolt, and only one thread is in engagement. You will observe that in that case, you have sort of permitted motion, that is, it can wiggle. So you can have a wiggling motion, you can have in and out motion. That is much easier. There is also possibility that the thread over here, the first thread that is coming in contact, could slip, and then the bolt and the nut or the tab is no longer in complete engagement. So what you need to make sure is the bolt is inserted so that at least 3 full threads are in contact. So that is the requirement for a proper engagement. So now sigma C is given to us, sigma P is known, DO is known, DC is known. So from this equation, we can find out the value of N. And this N has to be greater than equal to 3. If it is not greater than equal to 3, then you have to make it equal to 3. Minimum it should be 3. So you found out the value of N. And let's say, for the sake of discussion, this value of N is equal to say 5. Let's assume that you solve this equation and you have the value of n is equal to 5. Please note that the pitch of the thread on the screw has to be same as the pitch of the thread in the nut. So the pitch has to be the same. Pitch has to be the same, which means the length is equal to the pitch multiplied by number of threads. So you will have pitch multiplied by n is equal to L. Now please note, at this stage, just like any other design process, we have two values of L. L we obtain from the shear failure and L we obtain from the crushing failure. And you will get the maximum value out of this L obtained from crushing failure and L obtained from shear failure. Pick max value. And that will make sure that your design is safe. Okay, everyone clear? We have to find out the length of the nut. Length of the nut can be obtained independently by using two different equations. I can find out the length of the nut looking at the shear failure. I can find out the length of the nut looking at the crushing failure, and the length that I obtain, I should select the maximum length crushing obtained from crushing and from shear. Next step is the outside diameter of the coupler nut. Outside dia of coupler nut. So outside dia of the coupler nut is given as D, and that is given as, so I just want to tell you what that diameter is. This is this diameter. So this guy. That is sigma C is equal to P divided by pi by 4 D square. Okay, let me make sure I have used, okay, I need to use capital D. D square minus DC square multiplied by N. And please note, many a times the coupler crushing strength would be same as the crushing strength of the rod, or this could be different. So this crushing strength depends upon coupler material. So for an example, if you have steel bolt or steel rod and brass coupler, then you will use the crushing strength sigma C corresponding to brass. And this N will be same as the number of threads, an engagement that we obtained earlier. Now the next step is I want to find out the outside diameter of the coupler. And this dimension is given as D2. And that equation you can look at the tension failure. Now D1 is the inside diameter, and this inside diameter is nothing but this guy, as you can see, this dimension. So this is usually taken as D O plus some clearance. So usually 5 to 6 millimeter. If you look at the textbook, a textbook uses a slightly different formula for finding the outside diameter of the coupler nut. So what they do is they find the outside diameter of the coupler nut using the tensile failure. That is fine too. Then find D. And the reason for that is depending upon what type of failures you expect, uh, the cross-sectional, even though the cross-sectional area is going to remain the same, the values of the strength of material, the material stress values will change. So you can use different equations. Uh, that slight variation is absolutely possible. Now this process gives you all the major dimensions, and there are some other dimensions. Once you start drawing the turnbuckle, there are some dimensions. For example, what is the recommended clearance between the two ends? Then what is the thickness of the coupler, which is nothing but T. And this depends upon the design. Some couplers actually could have a continuous thickness. Some couplers could have the holes. So let me show you what I mean by that. So for an example, you could have a coupler that looks something like this. Or you could have a coupler that just looks like this. Then here is a turnbuckle. Here there is a hole. So what you do is to rotate this, you actually use a wrench and then rotate. If you have a coupler like this, you place a rod, inside, and then you use that rod to rotate. So depending upon the external designs, small variations are possible. Okay, any questions here? Any questions on design of turnbuckles? Okay, now the next natural extension is the design of power screws, and the equations that we are going to use for design of power screws are exactly same as design of turnbuckles. So rather than giving you a design process, let me work through a problem, because when we talk about power screw, we are going to talk about the design of screw, design of nut, length of nut, the number of threads. We will find out the torque. We'll find out the shear stresses because of the torque. We'll find out the normal stresses because of the load. And since the shear stresses and normal stresses are acting simultaneously, we will have to find out the principal stresses. So what we are going to do is, we will, I'll just take an example rather than giving you the design recipe. But the process is going to remain the same. Okay, let me take this problem. This is an interesting problem because in this problem, I would get to discuss a little bit of the bearing design too. So let's look at this problem. A vertical single start screw, vertical, it's a double start, vertical dual start screw has square threads with 100 millimeter of mean diameter. So this 100 millimeter is nothing but dm. The pitch is equal to 20 millimeters, and its supporting load is equal to 18 kilonewtons, and the axial thrust is taken by a thrust bearing of outside diameter OD 250 millimeter, inside diameter ID is equal to 100 millimeter, and find the force to be applied at the end of 400 millimeter lever to lift and lower the load. To lift, load. And the coefficient of friction, which is mu, is equal to 0.15, and coefficient of friction for the collar bearing, so this is for the screw, so screw friction, and coefficient of friction for the collar bearing is 0.2. This is bearing friction. So in this problem, if you look at this problem shows that we have a dual start square screw. So for an example, this is the screw. but this is a double start screw. So we have a double start screw, and then it has square threads, and then there is a nut, and the vertical load that is somehow supported. So the vertical load that is supported is 18 kilonewton. Now the load is 18 kilonewton, but the good news is the dimensions are given to us. So the mean diameter dm is 100 millimeters, pitch is 20 millimeters. So this allows me to calculate the helix angle. Please note, lead is equal to number of starts multiplied by the pitch. So 2 times 20, the lead of the screw is 40. Now alpha is equal to tan inverse of lead pi times dm. That is tan inverse 40 divided by pi times dm, which is 100. And once you solve this, you will see that alpha is tan inverse of 0.127. Now, what we need to do is we need to find out what is the actual torque that is needed to raise the load. Now, please note here there is a screw friction and here there is a bearing friction. So before we find out the total torque, we need to look into what are the different values of torque needed first to raise the load and what is the needed torque to overcome the friction. So total torque is equal to torque needed to raise the load plus torque needed to overcome the friction. So let's find out torque needed to, I'm going to call this TL and I'm going to call this TB. So TL is equal to W multiplied by mean radius multiplied by tan of alpha plus phi. Now phi is equal to tan inverse of the coefficient of friction for the screw, which is tan inverse of 0.15. And alpha is tan inverse of 0.127. So you can find out these values and then you can substitute these values in the equation, which is 18 kilonewtons multiplied by the mean radius, which is 100 divided by 2, 50 tan of alpha plus phi. So phi comes from here and alpha comes from here. And then the approximate answer is about 5 I don't have the breakdown. Okay, so I'll work out the next part, which is TB, which is torque needed to overcome the bearing friction. Now for the bearing friction, please understand how this bearing is going to look like. So you have this bearing is a thrust bearing. So think about it like it's like a sleeve. This sleeve has the inner diameter, which is 100 millimeter, and outer diameter 250 millimeter. So you have 100 millimeter and the outer diameter is 250 millimeter. Now, basically, when we look at the bearing design, uh, there are different theories to analyze bearing failure. And what I'm going to do is I'm going to use something called as the maximum wear theory. So I would say the frictional torque, T friction, is equal to the average radius. So which is nothing but sort of the mean radius for this guy. So I would say the frictional torque is nothing but the mean radius multiplied by the frictional force. And here is the justification for that. So imagine that this thrust bearing is acted upon by some force. This is acted upon by some force, say F. Now I want you to visualize the, the frictional force that is going to be perpendicular to this F, that is going to be mu times F. And this frictional force will actually be distributed on this entire area. But for the sake of simplicity, I'm going to assume the total frictional force is concentrated at the mean radius Rm. So I would say that the coefficient of friction multiplied by the total normal reaction, which is the vertical force, is acted at the mean radius. So I would find out the frictional torque as mu times F multiplied by R mean. Now the question here is, what is the value of R min? So you have two values of radius. The inner value is R1, which is 100 divided by 2. Outer value is R2, which is 250 divided by 2, 125. And Rm is the ratio or the average of these two. So Tf, which is nothing but Tb, is frictional torque. This is the frictional torque in bearing. Is equal to value of mu. Please note the value of mu for the bearing is different, which is 0.2, which is multiplied by the load, which is 18 kilonewtons, multiplied by the mean radius, which is 50 plus 125 divided by 2. and the total torque is TL plus TB is about 570 Newton meter. And I would encourage you to substitute the actual values and find out the values of the torque. Now we have to find out the force at the end of the 400 millimeter lever arm. To find force at lever is 400 millimeters. We know force multiplied by lever arm is equal to torque. So F is equal to 570 multiplied by 10 to the power 3 Newton millimeter divided by 400, and that should give you about 1500 Newton of force. So this is the amount of force that is needed if you want to raise the load. Now the tricky question here is what happens when we are going to lower down the load. Now when you try to lower down the load, please note the gravity is actually going to assist you. So when you try to lower down the load, the gravity is going to assist you. So the amount of torque that is needed to lower the load will be slightly less than the amount of torque that is needed to raise the load. And I just want to give you some sort of a justification for this. So please try to understand. What we have is, for the power screws, think about that we have a mass, and this is on an inclined plane. And if we want to raise this mass, which means we are trying to push this mass forward. So this is equivalent of raising the load. So what it means is you have to overcome first the frictional force, and I'm gonna show you the frictional force, which is opposite to the direction of motion. So you will have frictional force, and then you have the component of load, a component of weight, which is mg sine of alpha. So the force needed to raise, this is friction, this is external force. So the force that is needed to raise the load is addition of frictional force and the component of the self weight. Now let's look at the case when we are trying to lower the load. Same case, but now we are trying to lower the load. So this is, let me show here. So this is the F external, and now what is happening is you have the component of the self weight, which is mg sine theta or sine alpha, which is acting in the direction, and you have the frictional force, this is here. So this is lowering the load. So in this case, you have assistance from gravity. In this case, you have resistance from gravity. Now, whenever you are trying to look at the design, you will always design for the maximum possible loads, maximum possible torques, and maximum possible dimensions. So the case here in consideration is resistance from gravity requires you to have a higher torque, and that is what is we should consider when we are trying to solve for the torque required. Now with this, we can actually work out uh, a simple problem. And I'm trying to look through my notes for a second to solve a simple problem. Because there is, I have to look at the design of screw jack, but unfortunately, I don't think I will be able to finish the design of screw jack. But let me work out this problem. This is fairly simple problem that can be solved in the time that we have available. Okay. So design a screw clamp. Design a screw clamp with load capacity P is equal to 25 kilonewton. Now what do we mean by a screw clamp? So screw clamp is sort of another word for the C clamp, wherein what you have is you have a C-shaped clamp, and then here there is nut. Nut could be separate or nut could be integrated in the housing. Then you have screw, and then you have a small handle. So this is the housing. This is the screw. And this is the nut. So please note, nut could be integrated, or you can just drill and tap the threads. So in this problem, we have to find diameter of the screw, and height of nut. So the important dimensions are, we need to find out this diameter of the screw, and the height of nut is this. This is H, height of nut. Assume single start screw. Coefficient of friction is 0.25. And again, the stresses values, they can be given or they cannot be, they just say the material. But in this case, they give us the values of the design stresses. Sigma C is 120 Newton per millimeter square. Sigma B is equal to 20 Newton per millimeter square. And then tau is equal to 45 Newton per millimeter square. So in this case, they have given us the values of sigma C, sigma B, and tau. So I just want to show you how this can be used in particular application. This is exactly just like a C clamp. For an example, if you have a piece of wood or metal that needs to be held in place, you place this between the fixed jaw, one side of the housing, and the moving jaw, which is attached to the screw, and then tighten it. So what we do is, step one, design the diameter. Step one, screw dia DC design. And as you can see, the load that is going to come on the screw is compressive. So it will be designed for compression. Which is cross-sectional area is pi by 4 DC square. Now sigma C is equal to 120 is equal to 25 10 to the power 3 divided by pi by 4 times DC square. This gives me the value of DC about 17 millimeter. Now step 2, check for principal stresses. Now this step is slightly different. Now, and the reason I want you to understand is something like this. In this problem, we found out the core diameter. From the core diameter, I should be able to find out the outside diameter. And from core diameter and outside diameter, I should be able to find out the mean diameter. So at the end of step 1, I should have mean diameter, I should have outside diameter, and I already know the core diameter. So this is 17 millimeter. This is approximately 24 millimeter, and DM is 22 millimeter. These are approx values. So now I have core diameter, I have outside diameter, and I have mean. Please check my answers. So what I'm going to do is, first and foremost, I'm going to find out the value of the helix angle. So to find helix angle, now the equation for helix angle is alpha is equal to tan inverse of lead divided by pi times the mean diameter. Now please note, in this particular problem, unfortunately, the lead is not directly known, but the only thing we know, it's a single start. So lead is equal to number of starts multiplied by the pitch. Now at this point, what we should do is, we should look at the design data book and find out the screw that has the mean diameter of 22, which has square threads, and find out the value of pitch. So I will write the process here. Since pitch is not given, we select appropriate value of pitch from design data. Now, when you look at the design data book, you will see different types of threads. So if you look at the Acme standard, you will notice for the same mean diameter, so here there will be dm, and there will be different values of pitches. So pitch. So, and that depends upon the manufacturing process, that depends upon the type of gear. So you can choose any value. Typically, that value would be somewhere, that value will be somewhere in between DO minus DC. Approximately, pitch is equal to DO minus DC. And if you have access to design data book, you can just say, I looked at the table, say, given in the design data on page, certain page, and this is the value of the pitch that I'm going to use. If that is not directly known, then you can approximately say that my pitch is equal to D outside minus D inside. So D outside is 24 and core diameter is 17. So my pitch is 7 millimeter. And with this, I should be able to find out the value of lead, which is nothing but, again, it's a single start multiplied by 7 divided by pi multiplied by the mean diameter that we already got, which is 22. And that will give me the value of alpha. Now the next step is, I need to find out the value of torque. Torque is equal to W dm by 2, because that is Rm, multiplied by tan of alpha plus phi. W is equal to 25 kilonewton. Dm, we already know, 22 millimeters divided by 2 tan of alpha and phi. So alpha comes from this calculation and the phi comes from the mu value. So phi is equal to tan inverse of mu, which is tan inverse of 0.25. Once you find out the value Yeah, this is we are assuming single start, and I think that is given here over here too. So assume single start screw. Does that answer your question, Matthew? If it's a double start screw, then we will have to use lead is equal to 2 times the value of pitch. Then you'll find out the value of torque. And once you know the value of torque, you can find out the value of tau, which is torque divided by pi by 32, the value of d, which is 22, and that will give you value of torque. Again, sigma value is P divided by A, where P is 25 kilonewton. And please observe that our initial diameter was 16.34 or something, but we modified that to 17. So the actual value of sigma is going to be different. So from here, I get the value of tau, I get the value of sigma, and then I can find out the values of principal stresses. Sigma square root of sigma square plus 4 tau square. Tau is equal to 1/2 square root of sigma square plus 4 tau square. And these should be less than sigma design, and this should be less than tau design. And in this particular problem, the design stresses are given. If they are not given, we have to go back and look at the design data book and find out the values. The next part is the length of the nut. Step 2 is length of nut. And for the sake of simplicity, I'm going to assume the same material, assuming same material. So I can look at the shear failure tau design is equal to P divided by, and just for a second, I would like to go back to this slide. This is the same slide that we used for design of turnbuckle. If you look at the failure, since the turnbuckle has half of the thread on the left hand side and half of the thread on the right hand side, we used L by 2. So so actually there is something I want to clarify. This is actually L. This is not L by 2. Please note to correct this. This is L, but L by 2 is half of the total L is here and the other half is over here. So the value that you get is directly L. So please make that correction. So you will have from the equation of turnbuckle, we already found out that we have pi dc multiplied by L. Tau design value is given to us, which is 45, 25 kilonewton, pi times the core diameter 17 multiplied by L. So that gives me the value of L. Now I will find out the same value using the crushing. So crushing strength is 120. P value is 25, 10 to the power 3 divided by pi by 4. Outside diameter, you already know, which is 24 millimeter. 17 square multiplied by n. That gives me the value of n. I know the value of pitch that we determined 7 millimeters. So pitch comes from here, 7 millimeter from step 1. And I can find out the length is n multiplied by 7. And I have two values of L. I have this value of L and I have this value of L. And out of these two, select maximum. And that is how you will solve this problem. Next class, we will continue the discussion and I will look at solving the problem of a screw jack. That's it for today. I'm gonna stop recording, but if you have any questions, I would be happy to answer.